thank you to everyone who's managed to make it tonight to SciSoc's last event of term, but a brilliant one to cap us off, no less. Just a few housekeeping things to start with. So this event is being recorded in the manner that was stated on the sign-up form. So your face and voice shouldn't be visible unless your mic or camera is turned on. Fine if you want to have it turned on, but just to let you know. There will be opportunity to ask Mr. Homfray questions at the end, at which point you can turn the camera and mic on, and that's all good. Right, so now to introduce tonight's speaker, we have Mr. David Homfray, who is joining us to discuss tips and tricks for inventing the future. Mr. Homfray's worked in various innovation research roles. He's contributed to cutting-edge research in many different fields, ranging from neuroscience to fusion, and then currently in space technologies. He's a fellow at Institute of Physics at the Royal Astronomical Society and the British Interplanetary Society. So we really do have an absolute wealth of knowledge, both in the lab and outside of it, to come and share all of that wisdom with us tonight. So thank you very much, Mr. Homfray, and look forward to your talk.
Well, thank you. Let me just go and share my screen. Oh, that's not the one, of course. A window. There we go. Hopefully everyone can see that now. Yeah. So let's start. Well, first of all, I'd like to thank you for inviting me to talk this evening. I hope you'll actually enjoy it. It's going to be a little bit random, a little bit on various aspects of big science and engineering. My name is David Homfray, and I've really spent nearly 20 years in various aspects of big science and engineering, thinking about the future and how to try and build that and try and invent that. So this talk will discuss some of my passions, my research interests. The majority will be space and fusion, and showing that although there's a level of complexity there, and these activities are far in the future, they're not really the domain of just government anymore, and that small organizations or myself or you can also take part in those. So first of all, I'd like to make sure that we understand this is not me saying that we should predict the future. As Niels Bohr quotes, that it's extremely difficult to predict the future. And so what I'm suggesting is that you will have cool ideas and things that you want to do and things that you want to push forward. And so the best thing to do is invent them now, is to work out where you want to go and then try and build those steps to do that. And I want to put this in context of the work I've done, where I combine my two passions to try and build a fusion-powered interplanetary spacecraft, give you some of the ideas of the complexity behind that and the costs involved in that, and then show you how that big science and engineering is not just for the public sector. And I'll do that by showing you the emergence of the private sector in both fusion and human spaceflight. And then I will give you some tips and tricks that I've seen, both as a person that writes grants, but also now reviews grants as part of the satellite applications catapult. So really, it's probably the best to go back into where I've come from. So I am a absolute massive geek. That is the way it is. I'm a big fan of science fiction, and so I've always been thinking about what the future looks like. I was very fortunate when I left university. I got a job at the University of Oxford doing functional brain imaging. And it was this really great role of where I was a kind of technician and a kind of researcher. So at some points I could be building an MRI coil, or I could be building a shed, but also I could be doing research and looking at how to further MRI physics. I then went into the work I've been doing I had been doing for 17 years in fusion research, and again, a really good mix of being able to work on machines that are here now. JET, the Joint European TORUS, the world's largest magnetic confinement fusion machine, MAST and MAST-U, which is the UK's largest type of fusion machine, again a tokamak, but I will go into more detail of those. And then finally, this year, I've moved to a place called the Satellite Applications Catapult, and I'm working on a myriad of different projects, both in the upstream, so for instance looking at ion thrusters for spacecraft, and looking at downstream. So one of my projects, I'm also looking at using Earth observation to monitor deforestation in the supply chain, consumer supply chain. Where my passion really came from is this idea that we have this finite planet with finite resources, and for me, the two main methods of being able to manage resource better and become more sustainable is to have both high energy density, and therefore we look at the processes and methodologies that we use to create products, where most of the time nowadays you look at trying to minimize energy. And so with high energy density, you can now look at processes where you try and minimize the impact on resource, but also where we leave the cradle, as Tsiolkovsky said, one of the founding fathers of rocketry, where we leave the cradle of the Earth and go and find resources away from the Earth and bring them back. So really, I'd like to start now with that kind of story of how I got to this interest in the topic. And it started about 5 years ago, when I tried to, in a master's, combine both my fusion expertise and my space expertise. And I did that by designing a fusion-powered spacecraft. So you might ask why I want to combine fusion and spaceflight. And the solar system's really big. And in order to try and minimize the effect on human physiology and human psychology, you need to reduce the time of flight. And now, really, there's only a few methods to do that. If you're trying to accelerate a spacecraft, you either throw lots of stuff out the back, so you increase mass flow, or you make the stuff going out of the back at really high exhaust velocity. And because you want to try and maximize the payload, then you need to minimize propellant mass flow. And the only method therefore, is to increase the exhaust velocity. Now, the majority of current spacecraft use chemistry. So they're chemical rockets, especially to get out of the Earth's gravity well. They are relatively good to get to the moon, so that's exactly how the Apollo missions worked. And you can probably get to Mars with chemical rockets. However, they're energy limited, and therefore the exhaust velocity is limited. So when you then look at, for instance, other electrical power systems, they're either limited in power or specific power. And so specific power is how many watts do I get out of a kilogram of power supply. So if you take solar, it's actually got quite a good specific power. However, because it's proportional to the size, then you are limited in overall power. And of course, as you start to get further away from the sun, those solar panels become less effective. There are things called radioisotope thermal electric generators, and they are a little bit of radioactive material that gets warm, and then that thermal energy gets converted into electrical power. They are good for what they do because they have a long life. However, they are quite power limited, so you only tend to get a few kilowatts from them, and they're actually pretty poor when you look at specific power as well. And then there's fission. Fission you can get good powers out of, but again, they have relatively low specific power. Now, if you could harness fusion, you could really provide this compact, low mass, high specific power, and there's a potential to get over 1 kilowatt per kilogram from it. And that is a really important number, 1 kilowatt per kilogram, because that's what NASA deems as we would become really spacefaring species. So that's what I did. I spent a year or so looking at how to make a spacecraft which utilizes our current fusion research. So I looked at how we are doing it terrestrially, and then looked at how I could reduce mass by taking away things that are not needed. For instance, it doesn't need a vacuum vessel because the vacuum of space is just about good enough. I also found some key things. So if you combine the biological shield with a primary working fluid, you could really reduce mass, and you would keep it safe for any human occupants. But also running it at really high operating temperatures, so around 1,200 degrees. And the reason why I wanted to do that was because it made the thermal to electrical conversion more efficient, but also it meant that my radiators, to try and get rid of my low-grade heat, they could be a lot smaller. Fusion power density is proportional to the magnetic field of this actual machine. So you can imagine, and I'll go into a little bit more detail, but the plasma is contained in this magnetic bottle, and the higher the magnetic field is, the more crunch, the more plasma density you can get, fusion power density you can get out of it. And so once I did that, I worked with a number of people from United Kingdom Atomic Energy Authority, my old role. I worked with people from the Brazilian Space Agency, and a number of people around the country and internationally. And we decided that this thing probably could work. We could get, it looked like above 1 kilowatt per kilogram, and it meant that you could move a 700-ton spacecraft to around about a Jovian orbit, which is around 4 times the distance from the sun to the Earth, and you could get there in around 400 days. So it was really exciting to see that. But when you start to look at it, there is a big problem with this. It's really expensive, and there is a lot to do there. So currently there is no commercial fusion reactors. So if I wanted to build this thing, I would need to do all that research and all the costs that came from it. If you look at people that have moved from low Earth orbit into space, it's a handful of astronauts from the Apollo mission, and technically a few service missions to the Hubble Space Telescope. So this hasn't really been done. So there's a lot to do. It's really expensive. And to give you an idea of how expensive it is, if you take the Falcon Heavy, which is on the picture there, it costs around $2,300 per kilogram for launch. So a 700-ton spacecraft that you would lift and build in space would cost 2 billion just to launch the thing. And that's before all the prototypes, the research, the people. So I look at it and I think, well, why am I doing this? Because it's almost impossible for me to build. However, there is money out there. And so what I think would be interesting to look at is, how does the private industry get involved already in these massive science and engineering? Why do they do that if everything seems so far away and so expensive? So what I'd like to do now is show you the state of fusion research and space, and show you the emergence of the private sector getting involved. But before I do that, I want to tell you why I believe fusion is so critical to us as a species. So currently there's 7 billion people on the planet, and 2 billion of those have no access to actually electricity. They're using primary biomass as their energy source. By 2050, we believe that there's going to be between 9 and 10 billion people on the planet. But even if there is no population increase, then just to get those 2 billion people onto the grid, we expect we're going to need between 40 and 50 billion megawatt hours. Now, we can move to renewables, and that is a really important part of the energy portfolio, but we do need something else. We can look at nuclear fission, but we know the issues of nuclear fission. We know the long-term waste issues, and actually uranium is not in plentiful supply. So fusion is a real answer to this. It's got very high energy density. The raw fuel for it comes from seawater. So the isotopes of deuterium and tritium are the fuels that you fuse together. And you can get tritium, which is radioactive, from lithium, and deuterium straight from seawater. So to give you an example of that, for one person for 60 years, all you would need is a bathtub of water and 2 laptop lithium batteries, and it would give one person their entire needs for 60 years. And that's why it's so critical to use. So this is JET, the Joint European TORUS, and I have been, so I'm getting quite emotional now. This is one of the most amazing devices our species has ever built. I was engineer in charge of JET for around 7 to 8 years. It is the largest fusion machine currently on the planet. If you look at the diagram on the left, you see your standard European person to give you a sense of perspective. And on the right-hand side, you see a video of a superimposed movie of the plasma. And the plasma is being held in this magnetic bottle. There's a toroidal field and a poloidal field holding this tight. And that plasma is getting to around 150 million degrees C. And actually, we're trying to hold it. It's very much like trying to hold a jelly in your hands. So as you try and manipulate it one place, it squeezes through the other. And it's difficult to do, but we have done it. And to show you this, we have made fusion power. And in 1997, we ran a series of experiments using deuterium and the tritium fuel. And we got 15 megawatts of power out of JET. JET runs most of the year, but normally we use just deuterium fuel. And this year, they're going to move back to using deuterium and tritium fuel again. And so they're going to try and break those records. This is the next exciting fusion machine that's being built in the south of France. So, sorry, before the JET machine cost around 500 million to build. The ITER, to give you a sense of scale, I've put a little red circle on the right-hand side, and inside that circle is a van. That gives you an understanding of the scale of this machine. and it's now moving into the assembly period. It's cost around 20 billion to build, and for me it's the sign that we're moving from the discovery era into the delivery era. This is going to produce 500 megawatts of fusion power from only a 50 megawatts input. And that's what the Q entails. It's the ratio of the output over the input. And it's going to be the first time we actually see a burning plasma, where the actual reaction of the fusion reaction keeps that plasma going round. And it's incredibly exciting. But again, it's an expensive bit of machinery. Now, it's not just jet and it's not just ITER. There's fusion around the world happening. We have, on the left-hand side, we have the public sector. One thing that I was very proud of the work we did at the UKAA, and they're still doing, is recently the government gave us 220 million to work on a new machine called STEP. And this is really trying to make sure that the UK is at the forefront of commercial delivery. But there's also DEMO, is the European next step after ITER. On the bottom left-hand side, you have Korea, that believes fusion is so important, they have it in their constitution. And in the bottom of the public box, you also have the Chinese version. So I'm giving you things that are really expensive, but on the right-hand side, you see that the private sector are now getting involved. From private investment, over $1 billion have now been given to the private sector. Recently, Commonwealth Fusion has received 200 million. Commonwealth Fusion are a spin out from MIT, and they have got a very exciting idea with very high magnetic fields. You've got a couple here from around Oxford, both First Light Fusion and Tokamak Energy. And then you have the Canadian General Fusion that are using, you can almost imagine it as pistons crunching that plasma and then trying to create energy from that. So we've just shown from this really expensive devices that are in the government sector, somehow the private sector are starting to get funding and starting to build devices. So now let's have a look in the space sector. So this to me is very much old space. You have the Russians' Soyuz rocket, which is the greatest rocket of all time, in my opinion. It's had 1,600 launches above that. Who knows how much it costs to develop back in the 50s, but a real workhorse of space. But it's extremely expensive to launch mass, so $7,600 per kilogram. When you look at the Apollo missions, extremely high cost of development, and the private sector, although involved, were mostly told what to do. So NASA would come along and say, here's your design, I want you to build this for me. The International Space Station, again, very high cost of development. I've put that there because, well, it's just really cool. We've had people continually in space, a continual presence for 20 years. And then finally, I put the space shuttle. I have really mixed feelings about the space shuttle. The cost of development and the incredibly high cost to launch a kilogram, for me, I believe stifled the space industry for many years. Very expensive, very large costs. But then we move now into new space, where you look at SpaceX. They're trying to reuse all aspects of their spacecraft. They've had hundreds of launches. They're bringing the price down of the cost of development. They're bringing the price down on how expensive it is to launch dollars per kilogram. And that's really exciting. Even when you look at the Artemis program, which is NASA's program to get back to the moon, they're no longer telling the private sector or other organizations what to do. They're now saying it's a real partnership. Here are our requirements, and you tell us how you'll design that. And so a great example is the Orion service the Orion and the service module. Orion's being built by Boeing, and from their requirements, they gave the design out. The service module is from the European Space Agency, and it's been very much based on something they've done previously and therefore could reduce cost. And the lander itself is going to be based on a design either by SpaceX or Blue Origin, which is Jeff Bezos's company. And so this is really more about partnership than a big public government body trying to push their ideas. The gateway is very, it's an interesting one because this will be a space station in lunar orbit, which will make transport between the Earth and the Moon easier. And that's very much a collaboration between private and public money. And also the UK are also getting involved in that. And finally, I want to bring SpaceX's other spacecraft, which is called Starship. Starship will be an absolute game changer for us as a species because it drops the price of the cost of launch below $270 per kilo, below the $1,000 per kilogram. That is massively important because it really then makes the access for space easier. This will mean that now projects and missions will no longer just be the domain of government. So hopefully I've shown you that here are two examples of large, big science and big engineering, predominantly the domain of the government. There has been the emergence of the private sector and private sector funding. So I would suggest to you that if you do have a vision and it's in the future, there is money out there from people who may have similar interests to you. To give you a little bit more, the R&D from the world in 2020 is expected to be $2.4 trillion. And in 2017, just in the UK, there was $34 billion of investment out there for R&D. And as you can see by the graph below, you can see on the bottom, on the horizontal axis, the technology readiness levels. So when you're looking at 1, you're looking at very basic research. And as you get past 9 on the TRL level, you're getting something that is easy to manufacture and people can use it all the time. Where you see the red line, you see you see a kind of gap, and it's really difficult to get across that valley of death. But there you can see smack bang in the middle, this high growth entrepreneurs being able to tap in both government and in private sector investment. And if as another example, if you look at the the business enterprise, there's almost 23 billion out there in the pot for people to do R&D. So there must be tips and tricks. You have a good idea, you have a vision of the future, you want to invent it. So what are the tips and tricks that I've learned that enable you to do that? So first of all, it's about the team. You will have heard of individuals that are very famous, your von Neumanns or your Turing. However, if they hadn't had great teams around them, you will have never heard of those people. But it's not good enough just to have a great team. You need diversity both on a technical and on a human level. There are a number of reports that I've got up on this slide, which shows you if you have good diversity, your company will be more profitable. And non-homogeneous teams are just smarter. They understand facts better, they process those facts more carefully, and they tend to be more innovative. And so you need this diverse team. You need a mixture of technical people that are able to dive deeply into the problem, creative people to bring you back out and show you the big picture, and a few people that are process driven. We need to jump through these hoops. We need to go through these gates. You also need a combination of leaders, people that are happy taking risks and have urgency and passion, and then other leaders that have a caring and nurturing side that want to look after your team. Now, for me, a great example of this, and it's such a shame it's such a great example, because I have a lot of trouble with the name Atanasov. But Atanasov took Morchy and Eckhart to court in 1971 about the general purpose computer, and he won. He basically said that he invented the general purpose computer, and Morchy and Eckhart were taking advantage of that design. However, when you talk to people who are in the know about this history, everybody thinks it's Morchy and Eckhart. And that's because Atanasov never actually finished his design. It basically abandoned in a basement. He didn't have the team to build that whole device. And Morchy and Eckhart were brilliant about bringing diverse team together that actually produced the world's first general purpose computer that was available for consumption. But so you've got your team. Now it's about collaboration. I'm going to give a quick plug to the organization I currently work for, which is the Catapult Network. Their job is to try and create growth and profit within the UK. We've had thousands of collaborations. The particular network Catapult I work for is in the satellite applications, but there are other 8 elite technology centers, all looking at cutting edge R&D and building the partnerships and the collaborations where people can thrive and make money from their ideas. Some people tend not to collaborate to begin with because they're concerned about IP and try and make sure that their ideas aren't stolen. But I can't recommend enough trying to work with other organizations as soon as possible. Learn the ropes of how to work with them. You need to protect IP, but you also need to learn to collaborate, because once you've got something that is of interest to people, that is not the time to then try and work on how do I make these relationships? What are the agreements I need to put in place? So really learn to get into collaborations as soon as possible. And also, if you're going to apply for a grant, you find people that are good at writing them. So for instance, the Catapult has ability to help if you've got a good idea to make sure you have a grant and to can find the right pot of money to apply for. And it has never been a better time to do this. The UK has many opportunities and different avenues for you to collaborate and to apply for money. And again, a great example is SpaceX and NASA. So Elon Musk does not care about the International Space Station. Elon Musk wanted to build a rocket that could go to Mars. But the international NASA could provide billions of money to invest in SpaceX. SpaceX continued to build rocketry with Mars in mind. However, utilizing that money could service NASA to get their crew to the International Space Station. So it's a really good example of how people can work together with slightly different agendas, but to achieve a common goal. So to try and break this slide down, I thought everybody would know this quote, but apparently nobody does. Desmond Tutu once said, "There's only one way to eat an elephant, and that's a bite at a time." So no one is going to pay me my hundreds of billions or trillions to build a fusion-powered spaceship. There's only one way for me to do this. It is trying to break that journey up into a number of steps, and then try and make sure that each one of those steps has value to somebody. So I will look at so if we take the spaceship example, I might look at high heat flux materials, which is extremely useful for the automotive industry. A really good example here is RACE, which is the remote applications of challenging environments, which is a centre which was set up by the United Kingdom Atomic Energy Authority. They felt that nobody was going to invest the billions needed into getting all the way to the end of fusion. But they realized that part of those steps for fusion was robotics and remote maintenance. So they built a center and they harnessed all the cross-sector interest in robotics, and they've started to make money from those collaborations because they've split it into sections. And they can also then make sure that they understand what robotic needs are for fusion. So it's a really good example of looking at the big picture, which is fusion, and breaking it down. Even though you need to think big, those first few steps, try and make small bites. Try and make those steps small. Apply for small pots. Get a knowledge of how to apply. Make sure that you complete the work. And once you get that reputation, that you understand the picture, you understand how to apply, and you also then do what you'll say you're going to do, it makes it so much easier later on to apply again. Once you've split this up into steps, it is so vital to understand the story. And this is an issue I see a lot when I read grants and try and provide advice. You have people that rush into solutions. And so they'll come out and they'll go, well, here you go, here's an answer. And I'm going, well, so can you explain to me what the question is? And there's a little bit of confusion. But if you don't understand the question and you don't understand who your stakeholder is and what their value is, how can you ever sell your ideas? So it's really important to distill the story, be able to provide very roughly to them what you see as the future, the steps you need to take to get to that future, and then really accurately and concisely be able to show them that particular step that you're trying to apply for funding for, and exactly where that value is to them. And for me, one of the greatest examples for stakeholder requirements, well, nearly the greatest stakeholder requirement, is from Kennedy in his Congress speech in 1961. Where basically he said, "I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the earth." And so for me, that's really clear. Before this decade is out. So I know time is the important thing here, and I will have funding available to me to meet those time frames. I need to take somebody, take them to the moon and return them safely. So although I've got time constraints, that's not the only important thing. I can't just fling people and keep trying. I have to do it safely. Unfortunately, there was a surplus requirement in there, which is a man on the moon. Who cares whether it was a man or who cares what it was? It just needed to be one of our species that went and did it. But again, that is a really good distillation of what the question is, which enabled NASA and their Apollo mission to quite clearly see what they needed to focus on. You can't do everything yourself, especially when you're looking at these massive projects. And it's about taking these incremental steps. So we've already talked about Morchley, about him being taken to court. I don't consider him a thief when it comes to innovation. I think innovation is looking what's out there and utilizing those things and putting things together in order for you to achieve your vision. There's just no point in reinventing the wheel when there's so much to do. If people have exciting things that you need as part of your project or your vision, try and partner up with them. Use that collaboration. Let them take some of that heavy weight for you. But also, anything that you can buy off the shelf, so commercial off the shelf, you should absolutely do it. It's really important not to try and build everything yourself. I give you 3 examples here. 2 of them are United Kingdom Atomic Energy Authority, where Tokamak Energy is a private company, wants to do fusion. However, they're not going to do all of it. So they've looked at UKAEA's MAST U design for the compact spherical tokamak, where they've looked at the diverter, which is an exhaust system to get rid of some of the pollutants out of the plasma. So Tokamak Energy are not going to design their own diverter. They're looking at using diverters that are already there. Commonwealth Fusion Systems, the spin out from MIT that I've already discussed, they don't have a lot of background in tritium. So again, they're looking at UKAEA's really good background in tritium production to see where collaborations can take place, where they can use that experience that UKAEA has. And then, of course, you've got the Sierra Nevada Corporation, their Dream Chaser space plane. And all the thermal tiles from that have been designed and manufactured by NASA. So again, why reinvent the wheel? Just utilize stuff that's already been there. And then finally, and the final tip I have for you is to get other people interested. So find out who else can make value from your story, whether it's financial, whether it's public relations, wherever they can find value. And if you can, tell them your story, get them interested in it. And then if you need to, even help them get funded and get them started. Because if now 2 people are explaining the same vision, it will make it far easier to bring more people in and the snowball gets bigger. And then wherever you can, if you can bring the supply chain to get them involved, then you're really now starting to cook on gas. And a good examples here are SpaceX. SpaceX, for their Mars mission, needs to refuel in space. They've recently got $59 million worth of research funding from NASA, who, although don't really care about SpaceX's work, they do care about refueling, and therefore they're doing that work. And then for me, the greatest example is MIT. And so they had a clever idea of a thing called integrated circuits, which they managed to explain to NASA why they needed them on their Apollo mission to make computers smaller. And now they are ubiquitous, and we are talking to each other, and you are listening to me via integrated circuits. And they did that because they got NASA interested, they got money from NASA, and they were able then to really push that concept. So that's, for me, the tips and tricks. You build passionate, diverse teams, collaborate with everyone, break it down into valuable, pitchable chunks, understand the question and tell anybody who will listen to your story, align to funding streams, be flexible, beg, steal and borrow, and then try and get others some form of value from it as well. And then now finally, I'd like to just give you a couple of examples. Alan Bond is one of the cleverest people I've ever met. He's one of the 3 Rocketeers, UK Rocketeers. He started out very early on as being a world expert in a thing called the world ship. The world ship used normal propulsion that couldn't get past the speed of light, that is science fiction, to the nearest star. And therefore the spacecraft had to be big enough to have generations of people, be easy to maintain, and to be big enough to move people to another star. But he found the trickiest thing was to lift all of that mass out of the gravity well. And so he moved to working on a thing called HOTOL, which was a space plane. After a while, that had a number of issues. He started a company called Reaction Engines, and they designed the Skylon space plane. From that, they then designed the Sabre engine, and that's had millions of dollars of investment. And that has led onto a heat exchanger company within Reaction Engines. So you can see from the grand vision of these world ships all the way to a core business of being with heat exchangers. And then finally, my example, and this is really the last one. So I've published a technology roadmap. I have a technical working group, which is networking worldwide. We have fusion and space sector. When I was working at UKAEA, trying to find the fusion and space sector to work together. We have now just started a nuclear and space working group with some really large companies in the UK. I'm doing research on several sectors for cross-cutting technologies. And one of my bits of work at the Satellite Application Catapult is looking at space-based solar, which has manufacturing in space and things like high heat flux technology. And so these are examples of things that help me and enable me to see that vision of an interplanetary class power plant. And so I'll finish there. I hope you've enjoyed that little move through the kind of how to try and make money from your ideas and thoughts. If anything, I just hope you realize that science and engineering is really cool and there's lots to do. It's about passion. It's about working in teams. It's about thinking about the narrative, and it's understanding people and trying to work with them. And I think that's it. So I'd like to stop there. So thank you very much. And I think I've gone a bit over time, so I apologize for that as well.
Oh, no worries about going over time. It's really interesting talk. Thank you so much. I'm curious to have time for a couple of questions. I see there's already one in the chat from Levan, who asks, do you think by 2300s we'll be at the level of tech you see in the Expanse TV show?
Yes. So the Expanse is one of the better explanations of science fiction. So there is no reason why we won't have fusion technology in space by that point. So the Expanse is a really good example of very close science fiction. So I see no reason why not.
I have a question.
Yes, Alan.
Hi, David. My privacy screen was on. Didn't realise. I realised I was speaking from a little black hole there. The slide you gave earlier about JET and about the fusion reactors that are coming online currently and that are planned. First of all, when is that follow-on from JET in France that's being built? When's that due to come online? And I know this is a tricky question. When do you think we'll be having fusion power plugged into the national grid?
So So ITER, I will say, I think will be starting to get in the next 4 to 5 years. We'll have some form of plasma, and I think we're talking about actual fusion plasmas. So with tritium, will be in the next 10 years or so. However, I think when you look at the work that we've been doing at UKAEA on the STEP machine, STEP was very much looking at how do we really accelerate in through our designs. So and there's a person called Matt Perks on here who is working on STEP as well. But it was very much looking at how the private sector are accelerating through, and what can we do. So my feeling is I have absolute clarity that we will have some form of prototype for device that is close to commercial by 2040. And then if you were really clever, I think you could get to commercial in 2042, 2043, if you were being really clever about it. And then of course it's about building that supply chain. So I think it's feasible, but there could be big breakthroughs from the private sector that scares everybody and moves everybody forward. So we should be able to prove this absolutely by 2040.
Could I ask a question?
Yes, please.
How do you, I very much enjoyed your talk, but how do you persuade funders to move beyond the current crisis, whatever that is? It could be global warming. The current one's obviously coronavirus. There always seems to be a big thing to soak up loads of money before really exciting ideas.
Yeah. So you're quite right with that, and that was a frustration for me both when I've tried to apply for grants as well. What do you mean you're not listening to my idea? It's brilliant. Now it's about that flexibility. So one of the slides I gave was this level of flexibility. So it is looking at, we're very lucky now that there's quite a lot of pots out there through Innovate, through even through the Catapult can help you as well. And it's slightly modifying your little steps that you've broken down to have value to those people. So being flexible enough to kind of go in the direction you want to go, yet still having value to that stakeholder. So for instance, the work that I'm now taking on, although I think fusion is a way for spacecraft, I'm now starting to do a bit more work on space-based solar, on radioisotope thermoelectric generators and fission devices, because I'm able to help set the agenda, which gives me some of the infrastructure, which then allows me later on to then move in the fusion domain. So it's about having a level of flexibility, I'm afraid, and making sure you understand what the stakeholder, what they value, and trying to make sure that the optics of what you're offering is right.
Thank you.
Oh, yes, sorry. There's another question from Levan in the chat, asking about the impact of Brexit on your work.
So in terms of fusion, it is still to be seen. There is a lot of concern. Obviously, we've lost some of our access to the Horizon 2020 programs and the future programs. It was on the day Brexit was announced, JET and UKAEA was on the news at 10, as something of Euratom having to be one of the first things being sorted, because it's not just fission and fusion, it's the movement of radionuclides around the country. And so my feeling is it will be hampered. However, when you look at UKAEA, it is the world's largest fusion research centre, and the likelihood of Europeans not wanting to access that is inconceivable. When you look at space, the European Space Agency is outside that of the EU. So our relationship with the European Space Agency will remain unchanged. However, we will get hit by forever diverging euro to sterling. So generally it should be fine. The UK is very good at big engineering and big science, and I hope that we can ride over what I think was an unnecessary action.
Thanks for that. Any other questions? Oh, there we go. A follow up from Levan. Should we go to the moon or to Mars first?
So we should do both. So the picture of the gateway I showed you was a really important step for me. And when I heard NASA were committing to the gateway, the lunar gateway, I felt that we had a chance of having a continual presence past low Earth orbit. So the gateway is really useful because what it does is it's actually quite expensive in terms of propellant to get a spacecraft into lunar orbit. So if you have quite an eccentric orbit for your lunar gateway, it makes it a little bit easier for your spacecraft coming from the Earth. It also makes it a really good platform to then go to Mars, but also to land on the moon. And my feeling is we should learn to operate on the moon for a while building the infrastructure to get to Mars. So I think we should do both, but we should use the moon as a test bed.
So I mean, just to follow up on, do you think a kind of a base in lunar orbit is more useful than a base on the lunar surface itself?
So I think you'll do both, but it is a satellite. So a space station around in lunar orbit will mean you have far less propellant needs for spacecraft leaving Earth, and then there'll be points where that space station is close to the moon, can make an easy landing. There will be a base on the moon, but there'll also be a gateway. A gateway between the Earth and the moon. So I think you won't have a moon base unless you have a space station in an eccentric orbit.
Great. Another one from Levan. I think this is following on from the expanse question and something I had in mind too. So do you think the social issues will be similar to those in the expanse?
Yeah, so in one of the first slides when I was talking about why we need fusion and space is because of those distances, and I'm worried as much of the psychology as I am on the physiology of onto the human body. You can already see in world politics issues down to resources creating political situations, and you can see that increasing when you need more resources coming from out off the planet. And so I can see situations where the people that have the money that are able to go out off the earth to get resources will become continually wealthier and will increase those problems. So yes, there is a lot of issues there. And actually, one of the great things the British Interplanetary Society is doing is not only do they look at the technical side, they're also looking at what we as a species, what will we become, and what do we need to do in terms of regulation, and in terms of do we pay for air? Do you pay? So here I do not need to pay for my air, so it's free to me. So how do we give people the rights in space that you don't need to pay for here? It's a really complex question, and fortunately the British Interplanetary Society is an amazing place to look at both the technical side but also the human side of what happens as we colonize space. So go and check them out.
Will do. And kind of a second part of that question, which follows on nicely from where you just ended. Colonization of space in our solar system, will it change our species at all?
Yes.
And if so, how do you think?
So of course we are still very much learning what happens to the physiology of the human body. There were a number of experiments done on the International Space Station recently, where a set of twins were separated. One spent a year in the space station, one stayed at home, and they looked at the difference between those twins on the effects of their body, and they were significant. There we will, and some of the ways that we might think about creating gravity, for instance using centrifuge, basically rotating discs and sticking people to the outside of those discs, the effect of that is subtly different. Some of the work that I've looked at says that actually the best way is about 0.6 of a G. Again, that will have an effect on the human body, but even in the world now we see evolution of the species, and that will happen. And as you go into different environments, that evolution will continue to happen. But certainly you switch off gravity, it's going to go and change your body after a while.
Yeah, I think there was a follow-up paper to the twin studies released, I think 5 days ago or something.
Oh, was there?
Yeah, I think it was in Cell, maybe. I don't quite remember where it was, but basically it was saying that part of the issue was in the mitochondria and how that was affected by lack of gravity.
I could quite easily see that.
Makes sense, right? So, okay, well, I think, let's see if anyone has any more questions to come. I suppose, I'll just get one in. Do you think, I mean, because not everything in science obviously goes as well as you like it to, right? So when you said to your shareholder, oh, there is value in this, but then after 5 or so years, well, I mean, it just didn't work. We were just barking up the wrong tree, or it's just our experiments failed. So how do you recommend reconciling that?
I think, so first of all, don't think of it as failure. Think of it as a route that you have proven doesn't work. So whether you're doing a PhD or a master's, or whether you're working on a project, any experiment that you are trying to prove something, if you show it doesn't work, it is as valid as if it does work. It's a real pain in the arse if it doesn't work. So for instance, the spacecraft design, I was very fortunate that the plasma parameters seem to be okay. There's a whole bunch of reasons why it wouldn't work, and I can see them myself, and it requires further investigation. However, it is important to find the routes that aren't valid as much as the routes that are valid. There will be points, however, where you go for funding where you're unable to get your point across. And the only thing I would suggest from there, and that's happened to me on a number of occasions, and the only thing I would suggest that you can do is to try and look at the way you've pitched, how you've broken that step down, and to really consider, is the value that you have said that that stakeholder believes, and that's the reason why they would give me the money, somewhere you've failed there, you've made a mistake, and they don't have the same value as you think they do. And so it's about reflection. It's not worked. Why did I make those mistakes? How could I change it better? And then just, it does get easier. And that's why you have companies that can write grants for you, because they've made 1,000 mistakes. But don't expect to win every grant. Don't expect to win every grant. If you're hitting 20%, 30%, you're doing well.
Yeah. Some good life lessons in that sense.
Yeah. But it's a learning process. It's a learning process.
Okay, final one from Lavan, if you don't mind.
No problem at all.
Do you think there is a protomolecule out there?
So so it is almost inconceivable that we are the only sentient species out there. The universe is absolutely vast, and so it would be really surprising if there wasn't something out there. Us not seeing it is kind of an indicator that the speed of light is really, really hard set, and therefore things are really far apart. And so it would be incredible to imagine that this small speck in this vast ocean of the universe is the only place where there is any form of life. And I think actually, as soon as we see, I'm very confident that we will see life on Mars. And when I mean life, I mean something that reproduces cells, living cells. I think we'll see in some format. And I think there is really a high potential to see something slightly more complex in somewhere like Europa. Now, I'm not talking about sentience, but I am talking about many. You might be able to see many cells, creatures in Europa. Now, if you did see lots of life in terms of maybe things as complex as kind of viruses, if you were able to see those sorts of things, then I think you can start to believe that life is almost ubiquitous, and it's when and not if. I probably shouldn't have said the word virus, should I? Not in the current situation.
All right. I'm sure if there's a virus, there has to be something for it to use as well, so it's a good indication.
Exactly.
Yeah. So thank you so much for spending your evening with us, Mr. Homfray. I mean, it was amazing to hear your kind of journey and the steps you've taken, and also your opinions on the future of these really kind of big technologies, which could easily define the next centuries. So yeah, thank you once again for joining us, and thanks everyone who stuck around, and to Lavan particularly for so many questions. Good to keep the conversation
yeah. Thank you very much.
So yeah, recording will be made available in the coming days, in case you want to catch up on something, and also the last installment of our members quiz. So yeah, thank you all very much for coming. and we'll see you next time, and have a good Christmas break.
Okay, well, thank you very much.